Here's something that'll blow your mind. While our fastest computers still process data using electrons moving through silicon, we're on the verge of harnessing something infinitely faster: pure light itself.
You know what's fascinating about that? We've been stuck trying to squeeze more transistors onto silicon chips for decades, but using photons instead of electrons could completely change the game.
That's right. And the timing couldn't be better. Traditional computing is approaching what engineers call the quantum tunneling limit. We physically can't make transistors much smaller without electrons literally jumping between circuits.
So what makes optical computing such a promising alternative? I mean, beyond just using light instead of electricity?
Well, before we go any further, let's introduce ourselves. Welcome to Technically You, the show where tech isn't just explained, it's made meaningful. Today we're covering a revolutionary shift in computing, something that could take us beyond the limits of silicon chips. That's right, optical and photonic computing.
You've probably heard the term before, maybe in science fiction or research papers. But this isn't just futuristic speculation anymore. Photonic computing is real, it's evolving fast, and it could soon disrupt everything from artificial intelligence to space exploration. So buckle in, and we're about to fire up the lasers. So what exactly is photonic computing?
At the most basic level, photonic computing replaces electrons with photons to transmit and process data. Traditional computers rely on electrical signals. Think ones and zeros being carried by tiny charges across transistors and logic gates.
Now picture replacing that current with beams of light. These light particles, photons, don't have mass, they travel faster, and they can carry much more data per second through optical interconnects, like fiber optic cables, waveguides, or silicon photonics.
And here's the difference. Photons don't interfere with each other like electrons do. That means multiple data streams can be transmitted at once using different wavelengths, a technique called wavelength division multiplexing, WDM.
Now this isn't just a sci-fi idea, there's actual hardware being developed. The core components include waveguides. These are like light highways, guiding photons through chips. Optical switches and modulators. These control the path and properties of light signals. Photodetectors convert photons back into electrons for hybrid systems. Interferometers and resonators, used to perform calculations via interference patterns.
And let's talk materials. Unlike traditional semiconductors made of silicon, photonic components often use materials like silicon nitride, indium phosphide, or even graphene, each with unique properties for light control, thermal resistance, and wavelength compatibility. So, why is this technology so game-changing?
Let's compare. Modern CPUs hit clock speed walls due to heat and quantum tunneling limits. Photonic systems, in contrast, can process terabits of data per second, consume far less energy, and scale without melting.
Here's a real-world analogy. Think of electrons as cars on a single-lane highway. There's traffic, collisions, and stoplights. Photons? They're flying drones on multiple invisible lanes in the sky. They don't crash, and they don't slow down. So, where are you seeing this technology in use?
Right now, we're seeing applications in AI model acceleration. Companies like Light Matter and Light Elegance are building optical AI processors capable of performing matrix operations using light. Data center interconnects, reducing energy and latency across massive workloads. Edge computing. Think photonic sensors for autonomous vehicles or wearables. Quantum computing interfaces. Optical systems provide clean entanglement and measurement capabilities.
Let's not forget telecom. Companies like Intel, Cisco, and IBM are integrating silicon photonics into network switches and routers, allowing ultra-fast, energy-efficient data transfer inside and between data centers. Can you cover how does optical computing actually compute?
Yes, of course, in many of today's photonic processors, the core computation technique is interference-based computing. Light waves are combined in such a way that they interfere constructively or destructively. The outcome can represent different logic values.
There's also Fourier optics, where light patterns are manipulated through lenses to perform transformations. kind of like how convolutional neural networks work in AI. This is particularly useful for image processing and pattern recognition.
And a critical part, analog versus digital. Much of photonic computing today is analog, continuous light intensity or phase, but efforts are underway to digitize light logic circuits for integration with traditional computing systems. I hear there is currently a lot of research in chip development and a lot of industry progress being made.
At MIT, researchers have developed a photonic chip that can perform AI inference faster than conventional GPUs, all while using a fraction of the power.
And then there's IR Labs working on optical I/O to replace copper connections in CPUs. They're creating chips that transmit data optically across short and long distances with no electromagnetic interference.
Meanwhile, Intel's Silicon Photonics division is integrating light-based components onto chips using standard CMOS processes, bridging the gap between traditional electronics and next-gen optics.
But it's not all light speed ahead. Let's talk challenges. Miniaturization. Light can't be focused into arbitrarily small areas like electrons can. This limits how compact chips can be. Storage. You can't store light the way you store electric charge. Persistent memory is still a hurdle. Error correction. Optical systems are sensitive to environmental factors like temperature and vibration. Cost and complexity. Fabrication processes are still expensive and hard to scale.
And software? Most algorithms are built for silicon. Adapting code to exploit photonic architectures will take time, education, and entirely new compiler frameworks. So, what's next?
In the near term, we'll likely see hybrid architectures where photonics handle high throughput or parallelizable tasks, and electronics manage control logic, storage, and interfacing.
And as AI continues to grow, so does the demand for power-efficient, scalable processors. Photonics could be the key to unlocking AGI-level performance without drowning in heat and electricity costs.
Here is what is on the horizon in the future. We will have computers that don't need fans, wearables that process AI locally, data centers that consume 90% less energy, space missions with low heat, high-speed processors, new kinds of neural networks that mimic the brain using light pathways. Photonic computing could bring about a paradigm shift, like the move from vacuum tubes to silicon. The next computing revolution might not come with a whir. It could arrive with a beam of silent light.
That's incredible. Though I have to wonder about the timeline for all this. When might we actually see these technologies in practical use?
Well, some experts predict we'll see specialized optical computing systems in data centers within the next 5 years. But for consumer devices, we're probably looking at 10 to 15 years before significant integration.
That actually seems pretty reasonable given how revolutionary this technology is.
So while photonic computing may still be in its early chapters, the groundwork is being laid today for a truly radical transformation. And the next time someone tells you that tech has reached its limit, just remember, we haven't even turned the lights on yet.
Thanks for joining us on Technically You. Be sure to subscribe, share, and leave a review if you're enjoying these discussions about the future of tech. Until next time, stay curious, stay informed, and stay technically you.